Hi, my name is Eric Rye. I'm at the University of Maryland, and the title of this talk is IPv6 Hitlist at Scale. Be careful what you wish for. So while we perform no internet-wide scans ourselves in this work, kind of at its core, this work is influenced by and in a sense about internet-wide scanning. The reason that I say that is because since 2013, internet-wide scans have become kind of the default hammer that we hit a lot of nails with in the IPv4 internet because of a tool called ZMAP that allows researchers to scan every IPv4 address in under an hour. This supports a whole wide variety of applications. Over the same decade, however, IPv6 has sort of exploded in growth, but the 128-bit address space of IPv6 makes internet-wide scans impossible. So instead, what people do in the IPv6 world is build what we call hit lists of active IPv6 addresses to use for experimentation. And so what we decided to do at the outset was to try to create the most comprehensive IPv6 hit list possible. And we think that we've taken some steps towards that. To kind of give you the punchline up front, we passively collected a hit list nearly 400 times larger than the current state-of-the-art IPv6 hit list over the same time interval. However, this is not a replacement for current state-of-the-art techniques because the addresses that we discovered and have on our hit list are complement current state-of-the-art techniques. And then we asked, what can you do with such a large hit list? And we find both new benefits and insights that we can derive, as well as new potential costs and harms with having such large hit lists. So over the next couple of slides, I'm going to talk about how current state-of-the-art IPv6 hit lists are collected, and then I'll talk about our approach and how it's different from current state-of-the-art. In IPv6, you have to measure different parts of the internet differently. And if you want to find active regions, active parts, active addresses within the core of the IPv6 internet, you typically use tools like YARP, which is a stateless trace route. It sends out a lot of TTL, or in IPv6 speak, hop-limited probes that expire somewhere in the core of the internet, and we learn about what addresses are active from the ICMP error messages these packets induce. If you want to find active addresses that are associated with servers or home routers, you do something a little bit different. You use DNS records and domain lists to attempt to find active addresses. You might train target generation algorithms on lists of previously seen addresses in the hopes that they'll generate or predict some new active addresses. And then something that I've been involved with quite a bit over the last couple of years is finding active addresses in the IPv6 residential space. And you do that via focused iterative scanning. The key point here is that both when you're trying to find core internet infrastructure, as well as find servers and home routers that are active, you're using active measurements to find them. One question you might have after looking at the last couple of slides is, where are all the clients in this? We're finding a bunch of routers and servers, but where are the end hosts? And they're not there. And there's a couple of reasons for that. It's very difficult to find clients using active measurements because clients are often behind firewalls. So my smart TV, for instance, is behind my home gateway, which is running a firewall. Secondly, clients typically generate random addresses, and it's best practice for them to change those random addresses frequently over time in order to resist tracking. So because these addresses are fairly random and they're changing over time, they're hard to predict, and so they're hard for us to send active probes to. And so therefore, as a result, we find that state-of-the-art hit lists typically lack any kind of meaningful representation of client and host addresses. And so we took a completely different approach to try to find clients in the IPv6 space. Instead of using active measurements, we passively collected IPv6 addresses, and we did this by operating 27 network time protocol, or NTP, servers that were geographically distributed over 6 continents. We added these NTP servers to a project called the NTP Pool, which is a volunteer-run organization that allows people to donate their NTP servers to the NTP Pool to use to field requests for time from clients that are configured to use the NTP pool. Not all clients are configured to use the NTP pool, but a lot are. And so when a client makes a DNS request for an NTP server from the NTP pool, your server may get selected via DNS round robin based on a couple of different parameters. And so in doing this, we were able to accumulate a list of nearly 8 billion unique IPv6 addresses over a period of 7 months. Just as a graphical depiction of what we're doing here is we're running, again, NTP servers that are part of the NTP pool, and clients are querying our servers for time. We don't just get clients, we also see some things that we think are servers and things that we think are home routers, but in a lot of cases, the addresses that we're receiving at our NTP servers are client addresses. So I mentioned that there's both benefits and harms with collecting such a large hit list like we did in this study. So first, one benefit or insight is just that it's even possible to collect this number of addresses as someone who's not running a content distribution network or a social network. Each of these NTP servers was run on a cloud provider and cost $7 or less per month to run. So this is a very accessible way for security and network measurement folks to find IPv6 clients. Again, it's very difficult to find active clients in the IPv6 internet, and so we showed that you can find client addresses by using passive measurements rather than using active measurements. And finally, we're illuminating different parts of the IPv6 internet that previous state-of-the-art hit lists and active measurement campaigns just don't see. And one of the reasons that we know that we're finding different parts of the IPv6 internet has to do with address entropy. And so what I'm showing here in red is the lower 64 bits of some IP addresses that are on this router. And we see that there's lots of zeros. This is the case because in things like core internet infrastructure, things that are actively managed by network administrators, they have to type these addresses into the command line. And so they don't want to be typing a whole, things that are, highly have a bunch of entropy, lots of different characters. They typically will manually assign these addresses, and they'll have very low entropy, like the ones that we see here on the screen. Server addresses are sort of a mixed bag. So again, these are devices that are often actively managed by network administrators. And so we do a lot of times see low entropy addresses like this google.com web server that has a low entropy interface identifier or lower 64 bits here displayed in red. But we also see some things like this ESPN.com web server that are higher entropy. But finally, in the client or the nhost space, almost all of the time we see random high entropy addresses. And again, the reason for this is because it's best practice in IPv6 for clients to choose random addresses and to change those addresses over time in order to resist tracking. What I'm displaying here is a plot of our measurement, the current state-of-the-art IPv6 hit list and measurement that was run by some folks at CADA at UCSD. So in the green plot here, we have the CADA measurement, and the CADA measurement largely finds core internet infrastructure because of the way that it's measuring. And we see that the entropy plot here shows that the CADA addresses that it discovers are all very low entropy in that green line. In the solid blue line, this is the IPv6 hit list, which is run by some fantastic folks at TU Munich. They're both finding core internet infrastructure, but they're also finding a bunch of servers and some things in the home router space. And so we see the entropy curve here that they've got is quite a bit higher than the CADA measurement. And then finally in the black, we have our NTP passive measurement. These are the entropies of the interface identifiers that we discover during our experiment. And we see that it's the highest of all. I mentioned that there's also some cost and potential, privacy harms that are associated with generating these larger hit lists too. We discovered hundreds of millions of IP addresses that encode the MAC address in the lower 64 bits of the IP address. This is a type of address, a legacy type of address called EUI64. And the types of MAC addresses that we're seeing in these legacy addresses are things that are associated with IoT devices like Sonos speakers, Amazon Alexas, and Samsung smart TVs. And these types of addresses, EUI64 addresses, also present a potential tracking threat as well. In this slide, I'm showing a Huawei MAC address that showed up in 3 different Chinese autonomous systems over the course of the 7 months of our experiment. So this potentially represents someone moving between different networks, home cell networks, for instance, over time. This is potential like pattern of life or user profiling threat. So finally, to conclude, over 7 months, we collected nearly 8 billion active IPv6 addresses using NTP servers in a passive manner, the largest hit list to date. We found that our approach largely complements existing approaches. So again, this is not a replacement for existing IPv6 hit list approaches, but rather something that can be added on as well. We find that these larger hit lists provide both unique benefits and that we find different parts of the IPv6 internet that are not illuminated by active measurements, but at the same time, we also find some potential causes for concern. There are hundreds of millions of clients that are using these legacy form of addresses called EUI64 addresses that represent a potential privacy and tracking threat. So thank you for listening. If you want to know more of the details, I'd point to my paper, and happy to talk both in person and online. Thanks.